So we're looking at Unit 6, Skill 5 today, which is going to focus on graphing logarithms. In order to do this, we're going to go ahead and we're going to start by graphing an exponential function. So you guys should be pretty familiar with these. So I have here a parent function of an exponential, y equals 2 to the x. So you have that parent function, or you could plug in and build these things. From the parent function, these are some values that we're aware of, and we've extended the table a little further just to kind of look at what happens. So 2 to the third power is 8, 2 to the negative 3 power is 1 over 8, and our exponential equation of the asymptote is at y equals 0. So this is pretty familiar, okay? And then when you look at part B, it says the log function is the inverse of the exponential function. Okay? Based on the relationships between inverses, can we create a table for log base 2 of x? So notice that both of these equations have a base of 2. These are inverse equations. And so then the idea is, if you know what the exponential table looks like, and you know the properties of inverses, can we then go ahead and write this log table? So remember that inverses switch inputs and outputs our x and y values. So all of our y values or outputs previously would now become our x values or inputs. And all of our x values previously will now become these outputs. And then our equation of our asymptote used to be y equals 0. It will now be x equals 0. Again, all the x's and y's are changing places, so that will make that equation look a little bit different. What used to be a horizontal line is now a vertical line. And now what we're going to do so that we can visually see this difference is we're going to graph both of these on the same graph. So I'm going to put here this log function. Apparently, it would have this asymptote. And I'm going to try and plot these points. So an eighth negative 3, a quarter negative 2, half negative 1, 1, 0, 2, 1, 4, 2, and 8, 3. So this curve now tends to go like this. And this is the reflection of that exponential curve over the line y equals x. To see that better, we will actually put the exponential curve on here as well. So there's the asymptote at y equals 0, 1/8, negative 3, 1/8, negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. And hopefully this helps you visually see that inverse relationship, that these are reflections over that line y equals x. I'm going to draw that in here for you so that you can see that. And you can see they definitely look like they've been reflected over that. So our point being here that these log graphs we're about to create are created to exponential functions because of how a logarithm is defined. So we saw that in the last lesson. A log is defined by knowing your exponential properties, and those create this world of logarithms. They're the same information just written in a different format, and so we can see their equations graphically as inverses of each other. So just like your exponential equations, take a little space right here, each log equation is going to have a base. So I'm going to just write a couple of examples right here. Let's say that you were asked to graph any of these particular functions. All right, so I've written 3 different ones here. All right, so when I look at the first one, this logarithm has a base of 3. That means the 3 is not a transformation. It is the base, and the parent function for this would be log base 3 of x. For the second equation I've written here, 1/2 is the base of the logarithm. That means 1/2 is not a transformation of the function. It's the base that you would use for the parent function. And then lastly, 3. And so the parent function, if I was going to graph this equation, would start with log base 3 of x. Okay? All of our examples are going to be based on having a log base 2. So we're going to build the log base 2 parent function. Okay. And you have two ways to kind of build this. One is to understand logarithms really well. Some of you might really understand this concept and you understand the numbers that you'd want to plug into a logarithm with base 2. I would want to plug in things that are negative, 0, and positive powers of 2. So I would pick these numbers here. And then to get the y values that go with them, I would literally be doing the calculations. What is log base 2 of 1/4? Well, negative 2 is the exponent. I would put on 2 to obtain 1/4. What is log base 2 of 1/2? Negative 1. What is log base 2 of 1? 0. What is log base 2 of 2? 1. What is log base 2 of 4? 2. So one way to build this table is just to basically build a logarithm parent function. Okay. Option 2 is to take 2 steps to build this parent function and to first think about its inverse exponential function. So its exponent inverse would be the parent function for the exponents that had a base of 2 that we built at the very beginning of this unit. So we might know those a little bit better. This would be the parent function, for an exponential function with a base of 2, and then you could basically take the inverse of that to get the parent function that has log base 2. So two ways. You can either understand logarithms well enough to build it, or you can think about the exponential function and use its inverse. Okay, and all of our log parent functions have their asymptote at x equals 0. Like our exponential functions had theirs at y equals 0. So for this parent function, here's the asymptote. Okay. 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2. And so there that is. And again, this is a parent function. So our h value is 0 and our k value is 0 because there's not any shifting that occurred here. Our x-intercept we can see at the point 1, 0. Our y-intercept is none. So there's a vertical asymptote here that's stopping us from reaching or going past an x value of 0, so we never reach the y-axis. The domain is only on the right side of that asymptote, so it is all x values that are bigger than 0, or if you like to write that in interval notation, it's from 0 to infinity. And the range is all real numbers. And again, you should see the inverse quality here, that these are very similar to the domain and range of the exponential function, but they have switched, okay? This function is entirely increasing if we move across the graph from left to right. So we will have an increasing interval that includes the entire domain, so that's from 0 to infinity, and no decreasing interval. This is a function, and it does pass the horizontal line test as well, so it's 1 to 1. Again, you're not going to be responsible for rate of change here, and axis of symmetry is not applicable. Because this function continues to rise and fall infinitely, there is no minimum or maximum value. And since it's a log function, it has that vertical asymptote instead of the horizontal asymptote. So if you need to pause, take a minute to pause because we're going to keep moving through the video, but of course you can pause when you need. All right, so when I look at this first example, it's log base 2. All of our examples are going to be log base 2 here. Don't use log base 2 values if you're graphing a function that's log base 3. You would have to find a different parent function. We have an a value of 2 here, an h value of -3, and a k value of 1. This means as we go to adjust our table of values, we would want the x's to be shifted left 3. The y values would experience that vertical stretch and a shift up 1. Okay. So here's how our values would change. So I'm just taking the x values of the parent function, and I'm subtracting 3 from each one of those. And our asymptote's going to shift 3 to the left as well, or you could literally think of it as taking that value of 0 and adjusting it by the same transformation. Now I'm going to take the y values, and I'm going to go ahead and adjust those by multiplying by 2 and adding 1. And I'm going to go ahead and put this on the graph. So I have this asymptote at -3, vertical asymptote, so x equals -3, 2 3/4 -3, 2 1/2 -1, -2 1, -1 3, and 1 5. All right, so our h and our k values here, we had a shift left 3, our h was -3, and we had a shift up 1, our k value was +1. Our x-intercept did not come out in our table, but we can see that it does cross the x-axis. To find the x-intercept, we would set y equal to 0, and we would want to solve for x in this equation. So we would end up subtracting 1, and then dividing by 2, and then you almost feel at this point it would be guess and check to try and figure out what x do I plug in here to take log base 2 and get -1/2. But we're going to talk about different ways to solve this in a little bit of a future unit. So we'll leave this blank for now, and we can come back and we can solve it later. For our y-intercept, we're going to plug 0 in for x and see what the y value would equal. And we can just keep this in log format. So this is going to say log base 2 of 3. Now we've done some calculating logs, and we think of them as 2 to what power equals 3, but 3 is not a power of 2 that we know. So it's okay to keep this as it is, meaning we're just going to write that y coordinate in that log form. Our domain here is that x is greater than -3 or from -3 to infinity. Our range is all real numbers, or -infinity to infinity. This function is increasing over the entire domain, so the increasing interval is the entire domain with no decreasing interval. It is 1 to 1. We're not responsible for rate of change, and there's no axis of symmetry. There's no minimum, no maximum, no horizontal asymptote, and there's that vertical asymptote at x equals -3. All right, so we're going to do one more example that's going to include those horizontal stretches and compressions. So here we have a logarithmic function, and I'm actually going to rewrite that separating, sorry about that, I'm going to rewrite that separating that b value from that h and k value. So this is a log base 2. I'm going to have a 2 and then x minus 2, rather than writing it as 2x minus 4, so I can clearly see my h value. So I see an a value of -3, a b value of 2, an h value of 2, and a k value of -1. Meaning my x values are going to be compressed by 1/2 and then shifted 2 to the right. My y values will be reflected, stretched by 3, and then shifted 1 down. And if you remember from our prior page, the parent function values for the log function looked like this. And so I'm going to adjust those all according to these values. So each x is getting multiplied by 1/2 and added with 2. So that allows me these values here. And remember, normally our parent function has an asymptote at x equals 0, and in this case we've been shifted 2 to the right, so it will be at x equals 2. I'm now going to take the y values and adjust them by multiplying by -3 and subtracting 1. So here's my new values. I'm going to plot that asymptote and those points, and hopefully this looks how I expect. So I have this vertical asymptote at x equals 2. So I'm just going to do this in a little bit of a brighter color so it shows up a little bit better. All right, so there's my asymptote at x equals 2. So I have 2 1/8, 5. And I have 2 1/4, 2. 2 1/2, -1. 3, -4. And 4, -7. All right, so we see it curving a little bit away here like this. And then over here it's just getting closer to. And there was a reflection, so it makes sense that it's facing this other way. So from here, our h values and our k values. So we shifted 2 to the right for our h value, and our k value shifted things down 1. Our x-intercept did not show up in the table. So again, to find the x-intercept, you would set y equal to 0 and write the rest of that equation. And you'd want to get that log alone, so you'd add 1. And then divide both sides by -3. And again, you might feel kind of stuck here depending on how your brain works and how clearly you see about inverses, or sorry, logarithms. And we are going to work on that at a later time. So we're going to come back to that solving problem. So right now we're going to leave the x-intercept empty. For the y-intercept, we're going to take the equation and plug in 0 for x. And you can see from the picture that there is not, or from the graph, there is not a y-intercept, and you'll see here in our calculation how come that's true. We're going to get log base 2 of -4. This is not calculatable, so I can't just leave this there. We can't take a logarithm of 0 or negative because of the way exponents work. There isn't any exponent rule that produces those values, so that is undefined. And you can also see it in your graph that it never crossed the y-axis. The domain here is that x is greater than 2, or from 2 to infinity. The range is all real numbers. This entire graph is a decreasing interval, so no increasing interval, and the entire domain is decreasing. It is 1 to 1, and again, you're not responsible for rate of change, and the axis of symmetry doesn't apply here. There's no minimum, no maximum, no horizontal asymptote, and here the vertical asymptote was at x equals 2.